Let's explore efficiency and conservation at home so that we can understand how to save energy at home. Energy efficiency and conservation are oftentimes confused. They're related, but they're different. Energy efficiency is the amount of useful energy you can get out of a system. In theory, a 100% energy efficient machine would change all of the energy put into it into useful work. However, converting one form of energy into another form always involves a loss of usable energy, usually in the form of thermal energy. In fact, most energy transformations are not very efficient. The human body is no exception. Your body's like a machine, and the fuel for your machine is food. Your body is very inefficient at converting food into useful work. Most of the energy in your body is released as thermal energy. When we're discussing how we use energy, efficiency refers to the equipment or machinery that we're using. For example, washing machines all clean our clothes. However, some are designed to do so using less water or electricity than similar machines. Clothes come out clean from both machines, but one machine is more efficient in its way it cleans them. Not to be confusing, but conservation of energy and energy conservation are not the same thing. One is a universal governing law of science. The other is a term explaining behaviors we employ to use less energy. When discussing how much energy we use, conservation refers to how we behave while using that energy. For example, the owners of the most efficiently built home can still waste energy if they leave the lights on and the refrigerator door open while pouring a glass of milk. People who have older, less efficient appliances, however, can still save energy by using them wisely. So essentially, energy conservation refers to the things we choose to do that use less energy. The electronic devices that you use at home are consuming electricity, just like a car consumes gas. Schools and homes contain many electrical devices called plug loads that help you complete tasks, learn, or help occupants stay comfortable and safe. It's estimated that about 30% of the total electricity consumed by a school is used to power these electrical devices. Managing the use of such equipment can greatly reduce a school's electricity consumption. Many computers, TVs, DVD players, and other electrical devices use electricity even when they're turned off. This type of electricity consumption is known as a phantom load because it can easily go unnoticed. Phantom loads are also known as standby power or leaking electricity. Phantom loads exist in many electronics or electrical devices found around the house or school. Equipment with electronic clocks, timers, or remote controls, portable equipment, and office equipment with wall cubes all have phantom loads and consume up to 40 watts when turned off, depending on the device. Especially when they're massed together, these appliances should be plugged into surge protectors so that all of the power can be turned off when they are not being used. When shopping for a new appliance or lighting, look for the Energy Star label. It's your assurance that the product saves energy. Energy Star appliances have been identified by the U.S. Environmental Protection Agency and Department of Energy as the most energy efficient products in the home or classroom. Another way to determine the efficiency of appliances is to compare energy usage using energy guide labels. The federal government requires most appliances to display bright yellow and black energy guide labels. Although these labels don't say exactly which appliance is the most efficient, they provide the annual energy consumption and average operating cost of each appliance, so you can compare them yourself. To make it easy to compare appliances, all of these distinctive yellow signs are organized exactly the same way. The Energy Guide tells you what the appliance is and lists key features, including similar features across other models in the price range. It lists in more detail what the make and model of that appliance are. This sometimes includes different capacities and sizes. The initial price isn't the only price you pay, so the Energy Guide tells you the cost of running that device for a whole year based on average consumption and average energy costs. This cost range compares your appliance's estimated yearly energy cost to similar models. The cost range gets more specific when you look at more specific features. This makes comparison shopping a breeze. The energy cost is directly related to the consumption, or the amount of kilowatt hours. This estimated yearly electricity use tells you how much power, kilowatts, you've used over time, hours. The Energy Guide provides information for all appliances, not just energy efficient appliances. However, you can still look on the Energy Guide for the Energy Star certification stamp. This appliance is Energy Star certified, so it's more efficient compared to other models. This explains why when you look at the cost range for the annual yearly energy cost, this particular model is on the lower end of the range. A lower annual cost for energy means you're using less energy. You're being efficient. And by purchasing this model, you're making a conservative choice. We've seen a direct correlation between the amount of greenhouse gases in our atmosphere and the amount of trapped heat. Some of those greenhouse gases are carbon dioxide, water vapor, and methane. And although they are a small amount of the overall atmosphere, they have a big impact. Water vapor is always there, hasn't really changed the amount, but it's those carbon-based molecules that we can change the amounts. Carbon is abundant. It's everywhere. We are carbon. It has 4 exterior electrons that allow it to connect in a lot of great ways to create things like hydrocarbons, which are fossil fuels. Burning those fossil fuels brings that carbon out and releases it into the atmosphere. Carbon dioxide, even though it's less than 1% of our atmosphere, is one of the biggest contenders here. Human activities caused a measurable amount of carbon dioxide, especially since we started burning those fossil fuels. Most scientists are in agreement that carbon dioxide levels directly have an impact on our climate. To show the impact that carbon dioxide can have, we have 2 beakers at the same room temperature. I'm going to use Alka-Seltzer to add carbon dioxide directly into one of the beakers. The carbon dioxide is heavier than the air, so it falls to the bottom of the beaker. I'm going to turn on a heat lamp, heating each of the 2 beakers at an even rate. This represents the sun, sending radiant energy. Both beakers start to heat up, but the beaker with the carbon dioxide flowing into it starts to heat up at a higher rate, reaching a higher temperature. Normal air retains heat, but adding a little bit of carbon dioxide makes a big difference. When we remove that thermal radiant energy, both beakers are going to retain that heat, but we notice that the carbon dioxide beaker is going to retain the heat longer. So not only does it heat up quicker, it holds on to that heat longer. Carbon dioxide is a very powerful gas. Greenhouse gases get their name from the greenhouse effect. Here you can see sun's radiant energy is reflecting light off the earth. Some of that light makes it through the atmosphere. But then when the heat comes back up from the earth, as the earth releases that heat, it gets trapped. So we have trapped thermal energy in our atmosphere. If we heat up the air, we start to see changes in weather, and if we see long-term changes in weather patterns, we see change in climate. This handful of greenhouse gases determines how our atmosphere retains heat. Some of these gas molecules, like oxygen and nitrogen, have very rigid bonds that don't move easily. This makes it very hard for them to retain thermal energy. Whereas other greenhouse gas molecules such as water vapor, methane, and carbon dioxide have very flexible bonds. As radiant energy enters the atmosphere and infrared light, or light in the form of heat, tries to exit the atmosphere, it causes these flexible bonds to vibrate or resonate. This transforms that radiant energy into thermal energy, trapping it in our atmosphere. This is all part of a natural cycle called the carbon cycle, which takes carbon in different forms from the lithosphere, hydrosphere, atmosphere, biosphere, and constantly flows it. The lithosphere is the ground, it's the rocks, it's the minerals, it's the fossil fuels below us. We started increasing this flow of carbon in different forms from the lithosphere as we started to burn it during the Industrial Revolution. The hydrosphere moves a little quicker. We have to wait for the lithosphere to work at the rock cycle, or for us to dig it up, but the hydrosphere works the water cycle. So carbon dioxide that's been absorbed in water can create acidic water, can be rained as acidic rain. Fish and plants are part of the carbon that's in this ecosystem. The atmosphere is where we see carbon absorbed as carbon dioxide, as methane, as different forms of carbon. The atmosphere interchanges carbon with all different spheres: lithosphere, hydrosphere, biosphere. The biosphere is one of the smaller reservoirs. We're part of it. Animals, plants are made of carbon. When we pass, our carbon goes into the ground, our nutrients go into the ground, and we become part of that great circle of life. Animals or plants that died millions of years ago, their carbon was pressurized into new hydrocarbons. That's why we take plants from millions of years ago and burn them today as coal.